So this is the Chapter 3, Section 2 lesson video on the International System of Units, or SI units. So the International System of Units, or SI, is a revised version of the metric system that scientists use around the world. It makes a lot more sense than what we use in America, like feet and inches and gallons, and nobody knows the conversion factors. For countries that use the metric system, they all know them. So unfortunately, for those of us who live in America, this section gets a little bit harder than it should be because of our weird American units. So these are the basic SI units. So for length, we're going to use meters, which is represented by M, so no feet or inches, anything like that. For mass, we use kilograms, which is kg. For temperature, we use Kelvin, which is a capital K, no degree sign. Time is seconds. Seconds is abbreviated just S, not SEC. Amount of substance is the mole. We'll talk more about the mole when we get to chapter 10. And it's abbreviated MOL. That's real convenient. We get to drop one letter. Luminous intensity deals with the brightness of something. It's the candela, which is abbreviated CD. And electric current is the ampere, which is abbreviated a capital A, not AMP. In chemistry, we will focus on these top ones. We don't really use luminous intensity or electric current in general chemistry in high school. Now, when you get into upper level chemistry in college, if you take those classes, you will use electric current a little more, but still not so much luminous intensity that often. All right, so these are just the basic SI units. For my classes, make sure you know this chart because it will be on the test. So prefixes are used to show very large or very small quantities. For your prefixes sheet, it's important to remember the following. 1 prefix unit equals 10 to the x base unit. So in class, I gave you a prefixes sheet. If you lost it, you can print it off of my school website, or you can ask me for another copy. If I have any more, I'll give you one. So what is the difference in a prefix unit and a base unit? Because a lot of people get confused by that. A base unit is just a unit, like meters, liters, grams, seconds. Those are base units. A prefix unit is a base unit with a prefix. So instead of just meters, it's centimeters. Centi is one of your prefixes. So this is a prefix unit. Instead of liter, milliliter. So milli is a prefix. So this is a prefix unit. Instead of grams, it's kilograms. So kilo is a prefix. Instead of seconds, if you have nanoseconds, that is a prefix unit. Okay, it's important for you to understand the difference in a base unit and a prefix unit because otherwise you can't follow this. Now, I personally, if I was you, would write this on your prefix sheet. 1 prefix unit equals 10 to the x base unit, and I'll show you how to fill that in as we go. So this is just an example of a prefix sheet. All right, so here they have chosen the base unit to be meter, and it's obviously spelled kind of the English way. In America, we spell it M-E-T-E-R, I get that. But remember, it doesn't have to be meter. Like they chose to do meters for all of these, so they have kilometer, centimeter. But remember, the base unit can be anything. It could be seconds, it could be grams, it could be liters. So it doesn't have to be meters. That's just the one that I put into the PowerPoint. So the important things from this chart are the symbols for them and the powers over here. Okay, we won't really focus on this section much. And then this is only important because then you'll hear me say it. Like a lot of people, when they see this weird U, it's a mu actually. It's called micro. A lot of people get confused by that. So that'll at least help you know what I'm saying. One thing to note too is deca is DA, deci is just D. Okay, other things to note is mega is a capital M, milli is a lowercase m, and micro, like I said, is a mu. It looks like this, because I know it might be hard to see. It's like you make a U, but it has a tail in the front. That's all a mu is, and that stands for micro. So don't get mega, milli, and micro mixed up, and don't get deca and deci. Deca is DA, deci is just a D for the prefix. All right, now keep in mind, all of these prefixes are going to have a letter after them. So like if you see MM, that's millimeter. If you see, HL, that's hectoliter. So just be prepared to see something after the prefixes. You can't just have a, centi of something. It's got to be a centimeter, a centiliter, something like that. All right, I'm going to come back to this slide a lot just to show you where I'm getting my numbers. All right, so remember, 1 prefix unit equals 10 to the x base unit. So first we're just going to practice writing the conversion factors. We're not even going to do any math yet. We will, but not yet. All right, so we're just going to practice writing the conversion factors. So it says centimeters to meters. So remember, 1 prefix unit equals 10 to the x base unit. So I just follow this. So what do I start with? I start with a 1. And then I write my prefix unit. Well, which one has a prefix? Centimeters or meters? This one has the prefix. Okay, so I say 1 centimeter. Okay, so I wrote 1. I wrote my prefix unit, then equals 10 to the x. The x comes from your prefix chart. Okay, so I'm going to click back and just hope this doesn't block what we need to be looking at. So I need to find my power for centi. So I go here and I find centi or c, and I go over here and I see it's 10 to the negative 2. That's how I know my x needs to be negative 2. And then I put my base unit. Well, we already decided centimeters is the prefix unit, so meters has to be the base unit. So that's how you write a conversion factor. The SI prefixes chart, sometimes it's kind of hard for people to get used to. All right, so let's look at another one, then I'll let you try the last two. So we have grams and kilograms. So I start with 1. Remember, we're just going to fill this in. So I start with 1. So 1 of my prefix unit. So which has a prefix? Grams or kilograms? Kilograms has a prefix. So it's going to be 1 kg equals. So notice, here I started with the centimeter, which was the first one. Here I started with the kilogram, which was the second one. That's okay. It doesn't matter what order you go in. All right? It'd be like me saying 2 plus 2 equals 4, or 4 equals 2 plus 2. It's the same thing. It doesn't matter which side of the equal sign they're on. All right, so 1 kilogram, or 1 prefix unit, equals 10 to the x. So that means I need to figure out my x for kilo this time. All right, so I'm going to go back. Hopefully none of it's blocked. So I find kilo right here. I go across. Kilo is 10 to the 3. So I go back and say, okay, it's 10 to the 3. And then my base unit, which in this case is just grams. Just like that. All right, so here, you pause it and you try the next two, and then we'll look at it together. Remember, the difference in D and DA, D is deci. All right, so I'm going to assume you paused it and tried it on your own, so let's move on to C. So again, I'm going to start with 1 prefix unit. So which one has the prefix, seconds or nanoseconds? Nanoseconds has the prefix. So 1 nanosecond equals 10 to the x base unit. So I write my 10. I need to see what my power is for nano. All right. Whoops. Oh gosh, I just gave you the answers. Don't look at this. All right, so I find nano right here. I go across. It's 10 to the negative 9. All right, so I do 10 to the negative 9, and then my base unit, which in this case is just seconds. All right, so hopefully you got that one right. All right, moving on to our last one. Hopefully you've already paused it and tried it. So it's deciliters to liters. So I start with my little equation here. 1 prefix unit, so 1, which one has a prefix? Deciliters does. So 1 DL, deciliter, equals 10 to the x base unit. So 10 to the x. So I need to find out what my power is for deci. So I go over here and I say, okay, deci is 10 to the negative 1. So remember, you'll really want your SI prefixes sheet unless you have those memorized, which I don't think most of you do. All right, 10 to the negative 1 base unit, and so my base unit is just liters. Okay, so this is how you write a conversion factor using your SI prefixes sheet. Now in section 3, we'll go into how to actually use them in math, but for right now, we're just going to focus on can you write a conversion factor. All right, so hopefully you're catching on to this, because that sheet can be kind of tricky to use. Most people, they want to do it backwards. They want to do 1 with the base unit and 10 to the x with the prefix unit. So I'm telling you, write this on your chart. That way you'll always see it when you're trying to write a conversion factor. And there's our factors. All right, so we learned the base units like meters, Kelvin, things like that. But sometimes we have a combination of SI base units, and these are called derived units. Like y'all have all learned, volume is length times width times height. So meters, meters, meters is meters cubed. Or you may have learned density is mass over volume. Well, the SI unit for mass is kilograms, volume is meters cubed, so the derived unit would be kilograms per meters cubed. Sometimes they even get new names, like a kilogram times meters per second squared is called a Newton. You may remember that from physical science when we did things like force. Pascals comes for pressure. It's a Newton per meter squared. So you may see other units than just the normal base ones, because sometimes it's just a combination of them. And like I said, those are just called derived units. So let's talk about the difference in mass and weight, because a lot of people use them interchangeably. So mass is the amount of matter an object contains. The SI unit is kilograms. Weight is the force that measures the pull of gravity on a given mass, and the SI unit is newtons. So we just saw newtons on that derived unit. So what's the difference in the two? Well, since weight is based on gravity, it changes with location. And by that I mean location with a different gravity. I don't mean if you weigh yourself at school and then go home and weigh yourself, it's going to be much different. It may be slightly different because of variations in the scale, but the gravitational field should be the same at your house. Mass stays constant regardless of location. So here's an example. There's a girl on Earth. She said, my weight on Earth is 560 newtons. When she goes to the moon has about 1/6 the gravity of Earth. So now her weight is only 90 newtons. Now, does she look any different? No. She did not actually lose any weight. I mean, she did lose weight, but she didn't lose mass. She said her mass is always 56 kilograms. So when people actually talk about losing weight, what they really want to do is lose mass. They physically want to get smaller. Losing weight, you can be 1/6 of your weight just going to the moon, but that's not going to help you fit into that bathing suit for the summer. So like I said, when people say they want to lose weight, they really mean they want to lose mass, but when you lose mass, your weight will also decrease also. So that's why people tend to use them interchangeably. So the difference is gravity. Weight is based on gravity. All right, so temperature. The quick definition that your book gives in this chapter is that temperature is a measure of how hot or cold an object is. That is a very elementary definition. So I went ahead and gave you the real one that we'll learn later. It's the measure of the average kinetic energy of an object's particles. So hopefully from physical science you remember what kinetic energy is. It's the energy of motion. So the faster the particles are moving, the higher the temperature. So there's 3 temperature scales that are used. There's Celsius, which makes sense. There's Fahrenheit, which doesn't make any sense to ever use at all, but we use it in America. And there's Kelvin, which is your SI unit. So what's the difference in these? Well, Fahrenheit, freezing is 32 degrees Fahrenheit, and freezing of water. Boiling point of water is 212 Fahrenheit. The worst part about Fahrenheit is in America we use it. But I guarantee if I went into a Walmart parking lot and every person who walked out of Walmart, I asked what the boiling point of water is in Fahrenheit, half of them are going to say 100, half of them are going to say 200. And a bunch of them are going to say 132. Most Americans don't even know the boiling point of water in Fahrenheit. So I don't even know why we use it. Celsius makes a lot more sense because it's based on water's freezing and boiling points. So ice melts or water freezes at 0 degrees Celsius and boils at 100. And then Kelvin is based on 0 being the lowest temperature possible. So in Fahrenheit and Celsius, they can both have negative degrees, but Kelvin cannot. The lowest temperature is 0. So that's what it's based off of, is that there's nothing lower than 0 Kelvin. So you have 0 Kelvin, water freezes at about 273 Kelvin and boils at about 373 Kelvin. So again, Kelvin is helpful, Celsius is helpful, Fahrenheit just doesn't make any sense, and I don't know why we still use it in America. But they didn't ask me what I wanted to use, so I use whatever I'm given. So let's talk about that 0 Kelvin. Absolute 0 is 0 on the Kelvin scale. Kelvin temperature is directly proportional to the kinetic energy or speed of the particles. So that means if the particles go faster, your Kelvin temperature gets higher. If the particles move slower, the Kelvin temperature gets lower. If the particles stop moving, because that's of course the slowest they can go, so they have 0 movement, Kelvin temperature is 0. That's why it can't be negative. You can't go slower than stop. Alright, so if the particles are not moving, then Kelvin temperature is 0. Since the particles cannot go slower than stopped, the Kelvin temperature does not have any negative values. Okay, I do like to ask that question on the test. Why can Kelvin never be 0? Why can Kelvin never be below 0 or have negative values? And a lot of people like to tell me absolute 0 is the lowest. That's not explaining why. Remember, your explanation is that it's 0 when the particles are stopped, so since they can't go any slower, it can't get any lower than 0. All right, so let's look at some formulas. So remember, you'll have formulas on your formula sheet, and so you don't need to memorize any of these. So I'll click back to the slides that you can pick which one you think we need to use each time. So the important thing is some of you have trouble figuring out when to use what formula. Whatever you're looking for needs to be by itself. So like if I'm looking for Fahrenheit, I would find the one where degrees Fahrenheit is by itself. If I'm looking for Kelvin, I would find the one where Kelvin's by itself. Now the problem is, of course, there's two where Celsius is by itself. Well, if I give you Fahrenheit and ask for Celsius, you would use this one. If I give you Kelvin and ask for Celsius, you would use this one. Okay, so some people, like I said, they just have a little bit of trouble figuring out when to use which ones. And I understand that. I mean, I went through that too earlier in my life. So let's look at a couple of these. So it says, the normal human body temperature is 37 degrees Celsius. So we know we have 37 degrees Celsius. What is that temperature in Kelvin? So that means I'm looking for Kelvin. So if I go back, which one is looking for Kelvin? This one. So Kelvin is degrees Celsius plus 273. Okay, I'm going to click back just so you don't have to look at all that background. All right, so then I just plug in. So 37 plus 273 ends up giving us 310. Now, I'm super picky about this. Kelvin, I didn't get to choose it, but I'm picky about it being correct. Kelvin does not have a degree sign. Like, you know how you would write 37 degrees Celsius or 100 degrees Fahrenheit? Kelvin does not have a degree sign. Now, I don't mark it wrong in the beginning. I just scratch it out and tell you not to do it anymore. But try to make sure to get used to that. There's no degree sign with Kelvin. All right, so let's look at a couple more. Hopefully you know how to plug into formulas from physical science, so hopefully this is pretty easy. All right, so you may want to pause the video and try these real quick, or if you're not feeling comfortable yet, watch me do one or two and then pause it and try it. All right, so we have 77.2 Kelvin, and we're going to Celsius. So we have Kelvin, we're going to Celsius. So if I go back, we have Kelvin, we're trying to get to Celsius. So it's degrees Celsius is Kelvin minus 273. So then I just plug in. So my 77.2 minus 273 becomes negative 195.8. Whoops, I wrote 8. 195.8 degrees Celsius. Okay, so some important things to remember. Don't forget to put your unit. I'm a unit Nazi. I will always notice if you don't have it or have the wrong one. And Celsius and Fahrenheit can be negative. That's okay. Kelvin cannot be negative. So if you get a negative Kelvin answer, you probably did something wrong. But Celsius and Fahrenheit can both be negative. All right, so let's look at our next one. We have 120 degrees Celsius. We want to know Fahrenheit. Why we would want to know Fahrenheit, I have no idea, because it doesn't make any sense. All right, so I find my Fahrenheit. So Fahrenheit is 9/5 Celsius plus 32. All right, so Fahrenheit is 9/5 Celsius plus 32. Make sure you're following your order of operations, because we're going to multiply this fraction times Celsius first and then add the 32. Okay, you can't do Celsius plus 32 and then multiply or you get the wrong answer. So 9/5 times 120 plus 32. So when I put this in the calculator, I literally just put it in like this. Like I'll put in parentheses, 9 divided by 5, parentheses, 120 plus 32. That's how I put that in the calculator. If you don't have that fractions button, you can just put it in like this. So once I solve that, I end up getting 248, and my unit is degrees Fahrenheit. All right. Now the trickiest type of temperature is this part C. It can't get any harder than that, because if you notice, we're going from Fahrenheit to Kelvin. So if I go back, I can go from Fahrenheit to Celsius, but I can't go directly to Kelvin. So you have to use two formulas. That's why I say it's the hardest. So I can go from Fahrenheit to Celsius, then I can go from Celsius to Kelvin. Sorry. So Celsius is 5/9, Fahrenheit minus 32. So Celsius is 5/9 Fahrenheit minus 32. Now notice your order of operations. This time Fahrenheit minus 32 is in parentheses, so you're going to subtract first and then multiply by your fraction. Okay, so I'm going to do this first. So 5/9, my Fahrenheit is 56, minus 32. So when I solve that, I end up getting 13.33, but what unit am I going to get? I'm going to get degrees Celsius. The question didn't ask me for Celsius, it asked me for Kelvin. So then I just do one more. So I go back and I say, okay, well, Celsius plus 273 will give me Kelvin. So I do Kelvin equals Celsius plus 273. So 13.33 plus 273 gives me 286.33 Kelvin. Alright, and so that's how you do these. So you just got to make sure you're using the right formula. Make sure you're following order of operations for those annoying Fahrenheit ones. Don't worry, we won't use Fahrenheit very often in here because it doesn't make any sense. Alright, so let's move on. We're almost done with this section. So there's my answers. So last thing is energy. Energy, hopefully you remember from physical science, is the ability to do work or supply heat. The SI unit for energy is a derived unit called the joule, which is represented by a capital J. In America, of course, we use calories instead of joules, which doesn't really make any sense. So the conversion factor to get between calories and joules is 1 calorie equals 4.184 joules, because of course using joules makes a lot more sense. Alright, so section assessment, yay! What are the SI units for the 5 common base units used in chemistry? So remember, we have that chart at the beginning of the section, but we only use the top 5. So let's see, we have length. I may go out of order because I'm just pulling them from my mind. In meters, we have time in seconds. We have temperature in Kelvin, capital K, no degree sign. We have amount of substance. Is mole, and we have, what am I leaving out? Oh, mass, which is kilograms. Okay, so remember, we know that luminous intensity is candela and electric current is ampere, but we won't really use those in general chemistry. All right, what is the symbol and meaning for each prefix? So this is where your prefix chart comes into play. I'm not going to keep going back at this point, so just look at your own. So the symbol for milli is M, and then the meaning is the power of 10. So for milli, the power of 10 is 10 to the negative 3. All right, what's the symbol for nano? If you look at your chart, it's N. And what does it mean? Well, the power for nano is 10 to the negative 9. What's the symbol for deci? Be careful for deci and deca. Deci is D. And so what's the meaning? It's 10 to the negative 1. And then centi is C. And the meaning is 10 to the negative 2. All right, so hopefully you got those. All right, so number 3, it says list the following units in order from largest to smallest. So if you're looking at your SI prefixes chart, the prefixes at the top are the large ones, and it goes smaller as you go down. So what you need to do is find these and find which one is the highest on your chart. So you have milli, centi, micro, the base unit, which is liters, and deci. So if you look at your chart, the base unit, or liters, is above all the other ones. So our largest one in this case is liters. If you look right under your base unit, you will see deci. So deciliters is a little bit smaller. If you look under deci, you will see centi. So centiliter is even smaller. If you look under centi, you will see milli. So milliliters is even smaller. And if you look under milli, you'll see the weird mu, micro. Okay, so that's the order from largest to smallest from what they gave us. All right, so number 4, it says, what is the volume of a paperback book that's 21 centimeters tall, 12 centimeters wide, and 3.5 centimeters thick? Well, hopefully you remember from long ago, volume is length times width times height. So we just multiply. So we have 21 centimeters times 12 centimeters times 3.5 centimeters. So once I multiply all those numbers together, I get 882 But what's my unit? Centimeters times centimeters times centimeters is centimeters cubed. And there we go. All right, so hopefully you remember volume. I don't really go over that because I think you've learned that plenty of times. All right, so hopefully you got all those. So let's move on to our last one. All right. So it says state the difference between weight and mass. Since I don't have a lot of room, I'm just going to say it. Weight is based on gravity. It's your mass times the gravitational pull. Mass is just the amount of matter something contains. So in other words, mass does not change with location. Weight changes if the gravitational field changes. Okay, so weight is based on gravity. Mass is just the amount of matter something contains. All right, so number 6, it says convert 170 degrees Celsius to Kelvin. So again, I'm not going to click all the way back to the slide with all the formulas. So we're looking for Kelvin. So Kelvin is degrees Celsius plus 273. Remember, you don't need to memorize those formulas. I just have them memorized. So it's 170 plus 273. And so once I solve for that, I get 443. And my unit is just a big old capital K. Remember, no degree sign. No degree sign for Kelvin. All right, and then last says state the relationship between joules and calories. So that was just a couple of slides ago. It was right before section assessment, and we said 1 calorie equals 4.184 joules. So that's how we convert between calories and joules. All right, so hopefully that section was a little easier in section 1, section 3. Ooh, just get ready. Section 3 is probably going to be multiple videos because it is very long. However, I personally love section 3, but a lot of y'all do not because you don't understand it because you're not focusing in class. So make sure you're paying attention to this lesson video if you missed it in class, and if you'll follow the process, section 3 is not that bad.